to students. Today I am going to continue with the introduction and basic concepts of the first model of the heat transfer. And in this one, general one-dimensional heat conduction equation we have to take. In that we have to consider a one-dimensional system where the temperature varies along the only one direction, that is, and with the only one direction, and other two directions there is no variation of the temperature is considered. And here the temperature variation in the x direction we have considered, and along the y and z direction there is no variation, and the temperature profile for this one also we have considered. Then for this one dimensional heat conduction equation, this is a slab is considered, and for that we have considered the one element of length dx at a distance x from the one end, and where the qx amount of the heat is entering to that element, and qx plus dx amount of the heat is coming out of the element. And internal heat generation we are not going to consider here, and that can be given if internal heat generation is there, q generation is equal to q dot ax. Okay. Then one dimensional heat conduction equation, in that qx is energy conducted into the in LHS of the element minus Ka dt by dx, q generation energy generated within the element q dot a dx, and qx plus dx energy conducted out of the RHS of the element, that can be written as a qx plus dou by dou x of qx dx. Okay. Then dE by dt is change in internal energy, that rho Cpa dou t by dou t, and that can be written as rho Cpa dou t by dou t into dx. Then where rho is the density and Cp is the specific heat of the material, q dot is the energy generated per unit film, making energy balance for an elemental strip. For that elemental strip the energy balance is taken, and for that one energy balance means that for that elemental strip what are the energy entering into the conducted into the strip, plus the rate of energy generation within the strip, change in internal energy due to that energy generation, plus of energy conducted out of the strip. Then qx we have taken as the energy conducted into the element through x, and q generation as a internal heat generation. Initially we have to take that q generation also, and later without internal heat generation, that is we are going to eliminate. Then dE by dt, that is a change in internal energy per unit time, and qx plus dx is a amount of heat conducted out of the element through the RHS. Okay, then this qx is substituted as a minus Ka dt dou t by dou x, plus of q dot a dx as a internal heat generation, rho Cp dou t by dou x into dx minus Ka dou t by dou x at x plus dx, that is a qx plus dx. Here again this is substituted as same, and q dot a dx and rho Cp this one generation, and this is written as the qx plus dx will be the minus Ka dou t by dou x plus of dou by dou x of K dou t by dou x into dx. And here the minus Ka dou t by dou x and minus K dou t by dou x will be get cancels. Then after cancellation, then dx is term remains in all the terms, so that also get cancels. Only the a term also get cancels. Then the q dot remains on the left hand side. Then rho Cp dou t by dou t remains in the next term on the right hand side. Dou by dou x of K dou t by dou x will be remains the second term in the right hand side. Writing the differential equation, this equation we can write as a differential equation as a dou by dou x of K dou t by dou x plus of q dot is equal to rho Cp dou t by dou t. This is the differential power of equation. This is the one dimensional heat conduction equation. The above equation is known as one dimensional heat conduction equation in the rectangular coordinate system. This is the one dimensional heat conduction equation in rectangular coordinate system. Similarly, one dimensional heat conduction equation in cylindrical and spherical coordinates are given by 1 by r dou by dou r of r K dou t by dou r plus of q dot is equal to rho Cp dou t of rt by dou t. And one dimensional equation spherical coordinate 1 by r square dou by dou r of r square K dou t by dou r plus of q dot is equal to rho Cp dou t by dou t at r of t. Then the compact equation for this all the three coordinates, that is a rectangular cylindrical and spherical coordinates the one-dimensional heat conduction equations. Okay, then rectangular, cylindrical and spherical coordinates, one common equation that we can write. That common equation is 1 by r raised to n dou by dou r of r raised to n k dou t by dou r plus of q dot is equal to rho cp dou t by dou t, where n is equal to 0 for rectangular coordinate, n is equal to 1 for cylindrical coordinates, n is equal to 2 for spherical coordinate. Okay, then by substituting that, this equation will be modified, and for rectangular r will be replaced with the x, and for cylindrical and spherical it will be remains as the r radius, and in the replace x with the r variable we have to consider in this one. This is about the one-dimensional heat conduction equation derivation. Okay, that can be used for deriving the heat conduction equation for the particular solid. Then we have to take the three-dimensional heat conduction equation in Cartesian coordinates. General three-dimensional heat conduction equation in Cartesian coordinates. Here generally, if you consider the variation of the temperature along all the three directions or three dimensions, then we have to consider that variation of the temperature in all the three dimensions. Then that is the general three-dimensional heat conduction equation in Cartesian coordinates, and that is a Cartesian or a rectangular coordinates we are going to consider. Here this is a three-dimensional element we are going to consider, that is its length will be x, dx along the x direction, okay, dy along the y direction, and dz along the z direction. And there is a through this elemental strip, through all the three directions the heat is entering. Okay, the qx along the x axis, qy along the y axis, and qz along the z axis, the heat are entering into the element. Similarly, there is a internal heat generation, change in internal energy for this element. Then after that, the amount of heat leaving from the element, qx plus dx in the x direction, qy plus dy in the y direction, qz plus dz in the z direction. Okay, the three-dimensional Cartesian coordinates, whatever the element is there that we have considered, that is shown in the figure. Then for that energy balance equation, if you take in all the three directions, qx, qy, qz, all the three direction amount of heat entering into the element, plus of internal heat generation qgen, plus of all the amount of heat leaving from through all the three direction, qx plus dx plus qy plus dy plus of qz plus dz plus of de by dt. Okay, then where qx is minus k dy dz dou t by dou x, qx plus dx is equal minus k dou t by dou x plus of dou by dou x of k dou t by dou x dx dy dz. Okay, then qy is equal to minus k dx dz, it is the area. Okay, in the x direction we are going to take the area, in the x direction here it is the area, this is dy and this is dz, it will be area, surface area, that is the area normal to the heat transfer that we have taken. Similarly for in the y direction, the area will be the area normal to heat transfer, that is a dx dz dou t by dou y. qy plus dy, that is a minus k dou t by dou y plus of dou y of k dou t by dou y into dy dx dz. Similarly in the z directions we can take z direction, that is a minus k dx dy dou t by dou z, that is qz plus dz can be written as minus k dou t by dou z plus of dou by dou z of k dou t by dou z into dz dx dy. Then internal heat generation, okay, the rate of internal heat generation into the volume of the element, that is a q generation. Okay, the q dot dx dy dz. The change in internal energy per unit time will be d by dt rho cp dx dy dz into dou t by dou t. Substituting all the values in equation 1, we can write, okay, all this whatever the amount of heat entering into the element, plus of internal heat generation, plus of change in internal energy, that is equal to change in internal energy, plus of the whatever the amount of heat is leaving from the element. Okay, in all the three directions we can write that one. There is a minus k dy dz dou t by dou x, there is a heat entering in the x direction, minus k dou x dz dou t by dou y, heat leaving in the y direction, heat entering into the y direction, minus k dx dy dou t by dou z, heat entering in z direction, plus of this is internal heat generation, that is equal to the amount of heat leaving from the element, that is k dou T by dou x plus of dou by dou x of k dou T by dou x into dx dy dz. Okay, similarly in the y direction and z directions. Then whatever the change in internal energy is there, that is a rho Cp into volume of the element and change in temperature with respect to time, that is a rho Cp dV V into dou T by dou T. Then all these equations, if we rearrange that one, that is the first term minus k dy dz dou T by dou x. Then here if you separate that one, minus k dou T by dou x into dy dz will comes out. This side it will be negative, and this other side, that also negative equation term is there, then those will be get cancels. In the second term, that is a minus k dou x dz dou T by dou y. Here also minus k dou T by dou y dx dz, that will be get cancels. And this third term also get cancels here. And after that rearranging, this term only remains on the left hand side, and right hand side there is a minus k dou by dou x of k dou T by dou x, okay, plus of dou by dou y of k dou T by dou y, plus of k dou by dou z of k dou T by dou z into dx dy dz. Okay, here dx dy dz from the all the terms is taken outside, common, that is written here, plus of now it is change in internal energy, rho Cp dx dy dz dou T by dou T. Dou by dou x of k dou T by dou x plus dou by dou y of k dou T by dou y plus of dou by dou z of k dou T by dou z plus of q dot is equal to rho Cp dou T by dou T. If thermal conductivity k is constant, if thermal conductivity k is constant, it is not variable with the temperature, then we can take outside and send the other side. This k can be taken outside and send this side if it is not a variable, it's constant. Then this equation can be written as dou square T by dou x square plus of dou square T by dou y square plus of dou square T by dou z square plus of q dot by k is equal to rho Cp by k dou T by dou T. Okay, in this one, this equation, above equation, what is there? Here we can write as a dou square T by dou x square plus of dou square T by dou y square plus of dou square T by dou z square plus of q dot by k is equal to 1 by alpha dou T by dou T, where alpha is a thermal diffusivity. Alpha is the thermal diffusivity, that is the amount of heat diffused into the material. Okay, that we can determine from the conduction to the diffusion of the heat ratio, whatever is there, that we will call as a thermal diffusivity. Now whatever this equation is there, the equation 1, this equation is called as a Fourier-Biot number. Okay, in this above equation, the alpha is the thermal diffusivity of the material. The term rho Cp is known as a thermal heat capacity, thermal conductivity to the thermal heat capacity or thermal heat diffusion, that one we can take. Okay, then this is the equation. Okay, general three-dimensional heat conduction equation in Cartesian cylindrical Cartesian coordinates. Okay, rectangular coordinates. For the cylindrical coordinates, three-dimensional heat conduction equation in cylindrical coordinates is given by this equation, dou square T by dou r square plus of 1 by r dou T by dou r plus of 1 by r square dou T by dou pi square plus of dou square T by dou z square plus of q dot by k is equal to 1 by alpha dou T by dou T. Spherical coordinates, three-dimensional heat conduction equation in spherical coordinates is given by 1 by r dou square by dou r square rt plus of 1 by r square sin theta dou by dou theta sin theta dou T by dou T plus of 1 by r square sin square theta dou square T by dou theta square plus of q dot by k is equal to 1 by alpha dou T by dou T. The thermal diffusivity, that is defined here. Okay, it is defined as a ratio of thermal conductivity to the its thermal heat capacity. Okay, the physical significance of this one is the thermal diffusivity, physical significance, thermal associated with the propagation of the heat into the medium. How much quantity of the heat will be propagates or diffuses into the material, that is determined from this thermal diffusivity. Okay, then special cases we are going to take here. The special cases, what are there? The Laplace equation. Considering the three-dimensional heat conduction equation in Cartesian coordinates, this equation we have determined using Laplacian operator. Del square is the Laplacian operators. If you write this equation in terms of the Laplacian operator also, where del square t plus of q dot by k is equal to 1 by alpha dou T by dou T, where del square t is equal to dou square T by dou x square plus of dou square T by dou y square plus of dou square T by dou Z square. Okay, in heat generation, if the heat generation is absent and the process is steady, then in this equation q dot is equal to 0, dou T by dou T is equal to 0. Then we can write this equation as a dou square T by dou x square plus of dou square T by dou y square plus of dou square T by dou Z square is equal to 0, or this equation reduces to the del square T is equal to 0. This equation is known as a Laplace equation. By using the Laplacian operators without internal heat generation, or the steady equation, steady means variation of the temperature or heat transfer with respect to time is 0, then there is no variation. Then that one equation, we can, by taking that Laplace equation, we can write Poisson's equation. Here many cases here the temperature at any point in the material does not change with time. That is, if material temperature will not change with time, then dou T by dou T is equal to 0. Then the equation 2 becomes del square T plus of q dot by k is equal to 0. This equation is known as a Poisson's equation. Fourier equation, in the steady state, unsteady state heat transfer internally without internal heat generation is known as the above equation, reduces to this one, dou square T plus of that is equal to 1 by alpha dou T by dou T. This is the Fourier equation. Okay, thank you friends. We will continue in the next class.